Hello students, welcome to experiencetutor.com. Today's lesson is class 11th mathematics, complex number part 7.
Let us start with the welcome message. Dear students, welcome to our channel experiencetutor.com. In this channel, we will teach physics, chemistry, mathematics and biology for the students of class 10th, 11th and 12th and those who are appearing for the school board examinations and entrance examinations like IIT, NEET and all state level engineering and medical examinations. This course is organized according to different topics for each subjects. Therefore, it contains separate video for each and individual topics. Hence, it covers complete syllabus for CBSE, ICSE, ISC and all the state board examinations and engineering and medical examinations. You can also find the relevant topics for foreign school examinations like SAT, IGCSE, IB, etc. Enjoy your learning. Thank you.
Our first question is, if argument of z1 is equal to 2 pi by 3 and argument of z2 is equal to pi by 2, then find the principal value of argument of z1 into z2 and also find the quadrant of z1 and z2. So argument of z1 z2 is equal to argument of z1 plus argument of z2 plus 2 pi k. Now we can put the value of argument of z1 as 2 pi by 3 plus argument of z2 as pi by 2 plus 2 pi k to bring the argument in the principal range k is equal to minus 1. So we have to put k is equal to minus 1 here. Now the value will be 2 pi upon 3 plus pi by 2 minus 2 pi. Upon solving, we'll get minus 5 pi by 6. Therefore, z1 z2 argument is equal to minus 5 pi by 6 and it will fall in the third quadrant. Which quadrant? Third. Third quadrant. Our next question is, if z is equal to 1 plus I into 1 minus I upon 2 minus I, find the principal argument of z and also write the polar form of z. So we have z is equal to 1 minus I multiply by 1. So we have z is equal to 1 plus I. Multiply by 1 minus I upon 2 minus I. Now we can write the same as what we can do. We can multiply and divide the numerator and denominator, or multiply by multiply numerator and denominator by 2 plus I. So we can get it 2 plus I upon 2 square minus I square, which is equal to 2 upon 5 2 plus I. Is equal to 4 upon 5 plus I 2 upon 5. Principal argument of z is equal to z is equal to tan inverse y by x, which is 2 upon 5 by 4 upon 5, is equal to tan inverse half. Modulus of z is equal to under root 4 upon 5 whole square plus 2 upon 5 whole square, x square plus y square, so which will be equal to 16 upon 25 plus 4 upon 25. Upon solving, we'll get 20 upon 25, which is equal to 4 upon 5. Polar form. Polar form will be equal to in polar form z is equal to under root 4 upon 5 bracket cos theta plus I sin theta, where theta is equal to tan inverse 1 by 2. Our next question is, find the complex number if z into conjugate of z is equal to 2 and z plus conjugate of z is equal to 2. Now let z is equal to x plus I y. Therefore, conjugate of z will be x minus iy. So z multiplied by conjugate of z will be x plus iy x minus iy, which is equal to x square plus y square, and which is equal to 2. It is given. Therefore, we can write it as equation 1. Similarly, z plus conjugate of z is given 2. Therefore, we can write x plus iy plus x minus iy is equal to 2. Therefore, which implies that 2x is equal to 2, and ultimately we can write x is equal to 1. We can define this as equation 2. Therefore, by equation 1 and equation 2, we can get x is equal to 1, y is equal to plus minus 1. Hence, z is equal to 1 plus I or 1 minus I. Our next question is, if I zq plus z square minus z plus I is equal to 0, then so that modulus of z is equal to 1. So we have I zq plus z square minus z plus I is equal to 0. Then we can write so which implies that I z z square plus I plus z square plus I is equal to 0. Now we can take this common, so we'll get z square plus iz plus 1 is equal to 0. We know that when the product of two number is 0, then either of the number can be 0. If or we can write when this part is 0, then z square is equal to minus I, which implies that z is equal to z square modulus is equal to minus I modulus, which is equal to 1. Which implies that z is equal to 1, modulus of z is equal to 1, because modulus of z cannot be negative. And when this part is equal to 0, then we can write iz is equal to minus 1 and z is equal to minus 1 by I. If we multiply both numerator and denominator by I, then it will become minus I upon I square, and I square is equal to minus 1, so it will become I, which implies that z is equal to, or modulus of z is equal to modulus of I is equal to 1. In either case, therefore in either case, modulus of z is equal to 1. Our next question is, if z1, z2, z3 dot 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 zn are complex numbers such that modulus of z1 is equal to modulus of z2 is equal to dot 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 modulus of zn is equal to modulus of 1 by z1 plus 1 by z2 plus 1 by z3 plus dot 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 1 by zn is equal to 1, then so that modulus of z1 plus z2 plus z3 plus zn is equal to 1. Since modulus of z is equal to 1, we can write, which implies that z and conjugate of z is equal to 1, which implies that z conjugate of z is equal to 1 by z. So we can write modulus of 1 by z1 plus 1 by z2 plus 1 by z3 plus dot 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 dot, in the same way 1 by zn is equal to 1, which implies that modulus of conjugate of z1 plus conjugate of z2 plus conjugate of z3 plus dot 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 conjugate of zn is equal to 1. Now we can write as modulus of z1 plus z2 plus z3 plus zn and conjugate of whole expression is equal to 1, which implies that modulus of z1 plus z2 plus z3 plus zn is equal to 1, as modulus of z is equal to modulus of conjugate of z. Our next question is, if z1 and z2 are two complex numbers such that modulus of z1 is less than 1 and modulus of z2 is greater than 1, then prove that modulus of 1 minus z1 conjugate of z2 upon z1 minus z2 is less than 1. So we'll begin the sum by writing the given expression which we need to prove. So we have written modulus of 1 minus z1 conjugate of z2 upon z1 minus z2 smaller than 1. We can write, now we can write it as which implies that modulus of 1 minus z1 conjugate of z2 modulus of z1 minus modulus of z2 square. What we have done here, we have multiplied, we have done whole square in both the sides, so this is also a square, and 1 square is 1, so and then cross multiply, taking the denominator to the right hand side. So we got this expression. Now we'll simply simplify the expression, and on simplifying we'll get 1 minus z1 z2 conjugate, 1 minus z1 conjugate z2. Here we can write z1 minus z2 conjugate of z1 minus conjugate of z2, which implies that 1 minus z1 conjugate z2 minus z1 conjugate of z2 plus z1 conjugate of z1 z2 conjugate of z2 less than z1 conjugate of z2 this will be z1 z1 conjugate of z1 minus z1 conjugate into z2 minus z1 z2 conjugate plus z2 z2 conjugate. Upon simplifying, we'll get 1 minus z1 square minus z2 square plus z1 square modulus z2 square less than 0. Upon solving, we'll get bracket 1 minus z1 square minus bracket closed, then again 1 minus modulus of z2 square is less than 0. Upon solving, we'll get modulus of z1 square minus 1 minus 1 modulus of z2 square minus 1 less than 0. Now we can write the expression as z1 square is less than 1 and z2 modulus of z2 is greater than 1, which implies that z1 modulus of z1 is less than 1 and modulus of z2 is greater than 1, as z can't be negative. Now the next question is, prove that there does not exist complex number z such that modulus of z is less than 1 by 3 and sigma r is equal to 1 to n ar z to the power r is equal to 1, where modulus of ar is less than 2. So we can write the solution as, we can start the solution from here. So we'll write modulus of z 1 by 3 and sigma r is equal to 1, zn sigma r is equal to 1 till n ar z to the power r is equal to 1, where modulus of ar is less than 2. Now sigma r is equal to 1 till n ar z to the power r is equal to 1 can be written as this expression can be written as a1 a1 z plus a2 z square plus a3 z cube, plus in this way the whole expression will go till an z n is equal to 1. Again we can write the same as 1 is equal to modulus of 1. We have written the right hand side. Now left hand side will be a1 z plus a2 z plus a3 a2 z square plus a3 z cube plus dot 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 dot, and at last we can write an z to the power n, which is greater than equal to a1 z plus a2 z square plus modulus of A3 ZQ plus dot 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 modulus of an z to the power n, which is 2 1 by 3 plus 2 1 by 3 square plus 2 1 by 3 cube plus dot 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 1 by 3 to the power n to 1 by 3 to the power n, which can again be written as 2 as a common, 1 by 3, 1 by 3 square plus 1 by 3 cube plus dot 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 1 by 3n plus 1 by 3 to the power n plus 1 up to infinity. Next, this can be written as applying the progression formula to 1 upon 3 upon 1 minus 1 by 3, which is equal to 2 by 3 upon 2 by 3 is equal to 1, which implies that 1 is less than 1, which is not possible. Therefore, whatever we have considered that this expression is the initial expression is true is actually false. Therefore, no such complex number exists. The next question is an easy one. If argument of z is less than 0, then find argument of minus z minus argument of z. For this we will draw two graphs. In the first graph you can see the argument of z theta is equal to argument of z, and argument of minus z is equal to the second angle made with the x and minus z axis. In the second figure you can see argument of minus z is the angle between x and z dash axis, and argument of z is equal to the theta between x dash and z dash axis. Here we can see therefore argument of minus z minus argument of z will be equal to pi.
And this is the end of this topic. If you like this video, please subscribe our channel and give us a like sign. Please click on the bell icon so that you get automatic notification when a new video is uploaded by us. Thank you for watching our channel.